Okay, so as I said, I will continue the things for the boundary layer. So all are the parameters that you need to consider if you have the real fluid. Okay, so as I said, like boundary layer thickness, displacement thickness, momentum thickness, energy thickness, all the terms that you have to consider in terms of real fluid. So in this slide, we are going to know actually the same thing, okay? But we will focus on the real fluid now. It means we will have the stress. So it's not that much different, the things that I already explained. So before I said that normally when you have the body immersed in the fluid, we have two different types of force, right? One is the force that acts perpendicular to the surface. So we call this pressure force, or we call this hydrostatic pressure. Another one, we will have the force that acts tangential to the surface. It means if you have a moving body like ship, we have the force that will act tangential to the weighted surface and that will oppose the motion of the fluid, motion of the body. So if it's moving in this direction, so you will have the opposing force in the opposite directions. So it means that these force are actually called the shear force. Okay, so we have the shear force. So you know that the stress is equal to force divided by area. Okay, so if you have the force, you will have the stress. So we have to find out what is the shear stress. So the velocity profile, you know that the typically is like this, right? So it means that here the velocity is 0 and gradually it will increase, and at delta it will reach, at this point is u is equal to, u is local velocity, okay, 0.99 of u infinity or us, whatever you want you can say, and after that it will reach it. This is the u1. So it means the velocity profile is in this way. Okay, so so in this case, if you consider this boundary layer, we will have the shear. Okay, so we will have the force that needs to overcome. So in this layer, if you have the layer of fluid, another layer of fluid needs some force to overcome and to slide on the top of it. It cannot slide without any effort, okay, because we don't have any no slip condition. We have the no slip condition. If you have the slip condition, it means the layer can slip on the top of another one, then we will have the no viscosity, okay, no friction. But in this case we have, remember, no slip condition, so it cannot slip. So if you want to slide or glide, so you need the additional force, okay. So that force represents the stress. So if you consider that additional force that you need to overcome the resistance divided by the contact surface area, you will get the shear stress. So normally this is the in case of shear stress, we put the tau, okay. This is the normal stress, we use sigma. So this is, if you have the normal force, you have the normal stress, we use the sigma, and when you have the shear, we use tau. Okay, so that's the how we differentiate the notations. So the shear stress between any two horizontal layer is tau. Any two horizontal layer, as I said, layer means the layer of fluid, and when if you consider the boundary layer, we can consider the boundary layer is consist of numbers of horizontal layers that try to slide over each other, right? So it of course it cannot the slide without any effort, because it's a no slip condition. It has the viscosity, it has the frictions, so it needs some additional force, okay. And due to the additional force, if you divide it by the contact surface area, we will get the shear stress. So let's consider the shear stress between the any particular two horizontal layer is tau, okay. And for a Newtonian fluid, as I said, the Newtonian fluid is that fluid where the stress, okay, is proportional to the velocity gradient. Okay, velocity gradient. In this case, if you can see that the velocity gradient is nothing but the strain. Okay, so strain and stress, you know the strain stress relationship. Stress divided by strain is equal to Young modulus of elasticity, right? So similar thing we also have in case of fluid. We have the shear stress divided by, we have the shear strain. We call this strain rate of course is proportional. So this one Newtonian fluid is actually is within the is similar like elastic zone. Okay, it means the stress is proportional to strain. So Newtonian fluid is those kinds of fluid where the relationship between stress, shear stress and the strain is actually proportional. So you can write for a Newtonian fluid, the relationship between the shear stress and the dynamic viscosity and the rate of shear strain is like this. So you know that the stress is proportional to strain, epsilon. Okay, so we call this stress is equal to E epsilon. This is from the solid mechanics. Okay, but in this case fluid mechanics, in this case we have a stress. I will explain later why I put 0 here. Then is proportional to, in this case stress is proportional to, instead of considering the strain we call this rate of shear strain. It means rate of shear strain means how the deformation, it means how the velocity will change with respect to the position. It means if you move away from the wall, how the velocity will change. That is the strain in this case. Okay, so we measure the strain in terms of velocity change, or we call this velocity gradient. So Newtonian fluid is that fluid where the shear stress is proportional to the velocity gradient. You can also say that where the shear stress is proportional to the rate of shear strain. You can actually explain in different ways. Actually meaning is same. So if you want to make the proportional sign is should be equal, you need to put a constant, that is the dynamic viscosity, where we put the E, Young modulus of elasticity. In case of solid mechanics we need to put the viscosity. So this will define how much is the value, how to relate this and this. So for different fluid we have different mu, dynamic viscosity. So this is the definition of Newtonian fluid. Okay, so what is the wall shear? You can see here, instead of considering shear stress is a very big thing. Okay, so it will change with different positions. So we consider the stress is as a wall stress. It means at the wall when the y is 0. So where is the y is 0? It means where is the y is 0? At the wall condition, right? So at this wall here, so your stress is tau naught. Okay, and this gradient is the rate of shear strain. As I said, you can call it velocity gradient. You can also call it the rate of shear strain. Strain, you remember that the change, right, in the velocity in this case. So the velocity gradient, it means this gradient is very steeper in case of turbulent flow. It means the velocity gradient, the velocity will change abruptly. On the other hand, in case of laminar case, we have the is not that much steeper as we can get for the turbulent flow. So and also it said that because we have the stress, you need the force to overcome it, right? So if you need the force, this force is actually, experimentally we have found that this force proportional to the area, that is the area of contact, and the velocity of the plate, and inversely proportional to the distance between the moving plate and the horizontal or stationary plate H. So it means that this shear force in this case can be considered as U infinity is free stream velocity, S is the surface and surface area, and there is the H. So what is the H in this case? As I said, if you have this is a stationary plate, and we have this another plate that is moving with a velocity. Okay, so we will have the velocity in this case U infinity, or just you consider the velocity is moving, so we are not focusing on the how much the velocity of the plate. So but here we have the free stream velocity is U infinity. Okay, so then that is the distance here to here, that is the H. Okay, so it said that that is inversely proportional to the distance between the moving plate and the stationary plate. So we have these two plates, one is stationary, another one is moving. So honestly, if you have this moving plate, so we have this velocity profile is like this. Okay, so we define in this way, and H is the distance between these two plates. Okay. Okay, so any questions? No. Okay. So this is actually the same thing that I said last time. I said about the boundary layer thickness. Now it's come to the shear stress and shear strain. So what is the Newtonian fluid? But you will get know more on the Newtonian fluid later on in this slide or maybe next slides. Okay. So I hope oh, some problem. You are clear about this shear stress and shear strain, and we have this relationship. If you say how is possible to get this relationship, so this relationship is we got it from the experiment. Okay, from the experiment it shows that the relationship is like this way. We can establish the relationship. Okay, so other slides here actually represent the same that I already mentioned: the boundary layer, the displacement thickness, all the things. Okay, so again, because some say that you haven't understand uh, the concept of this displacement thickness or boundary layers or momentum thickness. So here are some slides that explain or re-explain the things in more deeply. So first we focus on the boundary displacement thickness. It's not the boundary layer actually. We say actually the slide should be displacement thickness. Okay. Anyway, so if we had a uniform flow equal to that of the boundary layer, the surface would have to displace a distance delta star in order to produce the reduction. This distance is called displacement thickness. Again, I am saying the same. Okay, if you have uniform flow, and this is the real fluid, real case stationary part. Okay, it means this is a stationary plate and this one is the moving plate. So moving plate is moving at a velocity of u infinity, but it means that we consider the free stream flow. So if you have these two combination, you expect to get the uniform flow. It means the flow should be uniform, but because we have the boundary layer, so flow will be not uniform if you are focusing on within the boundary layer thickness. Okay, if you consider this is the delta boundary layer thickness, so we will have the velocity here should be this dashed line, shaded line is actually the loss. Okay, so the loss at this point, how much? U infinity minus u. At this point, that should be u infinity minus, if you consider u1, u2, u3, you can write like u infinity minus u1, u infinity minus u2, u infinity minus u3. So you have all the shaded layer is the loss. You cannot get this flow. So if you have the loss of flow, you have to regenerate, right? So if you want to regenerate or replicate this loss, you need to consider this additional dimension. So remember that that will replace this shaded area is equivalent. Okay, so the flow rate for this additional part should be equal to the loss within this shaded part. If you can find out if this is the delta star, that is the additional dimension you have considered, so you will get extra flow. So this extra flow will be should be equal to the loss in this case if you have the real fluid or the velocity loss. So how we can consider this expression is already explained later last time. Okay, so again I'm trying to explain. So let's consider a strip B in the boundary layer. So here we call this strip B. The thickness of this boundary layer, sorry, this is a loss. The layer is dy. So if you use this one, so how much is the loss for that strip? So loss means is we consider the mass flow rate, mass by time, that is a rate, right? A change of mass per second per unit time. So that should be rho AV. You know that m prime, m dot should be rho AV. So in this case, you have the rho and u, in this case the velocity, and the area in this case should be dy multiplied by 1. Okay, so that is the value you will have, the general expression. Okay, so now you have the loss. How much is the loss? So this is a general expression. I am not just for, if you consider one strip, so you will have this much loss. So if you want to consider the total loss, okay, so because the velocity decrease like this way, we call this velocity defect. As I said, you can consider velocity loss, you can say velocity defect. So how much is the reduction flow? Reduction in the flow means you should have this u infinity, but you are getting u. So how much is the loss? Should be like this. So this one expression last time I already put directly. So because normally you should get this flow, in this case the flow loss is u infinity minus u. You can write it directly, okay, just to make sure that what this is the loss. It means they just consider u infinity minus u should be the loss. So the same thing they consider here, u infinity minus u should be the loss. So this u is actually the local velocity, okay. Don't be confused about capital U and small u, because this should be capital U, okay, because there are some discrepancies because these are taken from, I don't know, maybe from other books. So this should be capital U, okay. You should be consistent. This is u, so this should be capital U. Otherwise some might be confused, okay, it's small u, this why is capital U. You need to understand the basic thing. Okay, so this is the loss, as I said. So it means this is the expected flow, but now you are getting this much flow, so this is the loss, and this should be replaced by uh, this part, right? We said that this should be replaced by this. So how about this one? If you have this displacement thickness delta S, so extra flow that you will get is this much, right? So same like this UAV. So in this case we have the instead of thickness is delta star multiplied by 1, because the breadth is 1 in this case. You have the U infinity flow. So if you sum up, it means you need to this should be equivalent to this one. So if you simplify it, you will get the displacement thickness in this way. Okay, so we call the displacement thickness is the thickness, the additional dimension, the distance. You can say in different way that your boundary need to move, that you need to consider in your new design to replicate or replace the velocity defect, to replicate the velocity loss, to replicate the loss of flow that we are not getting in our design due to the boundary layer definition or boundary layer problem. Okay, so if as far as you understand the thing and you can write in a proper way, there should be no problem. Is it okay?
Okay, I understand now.
Okay.
Okay.
Okay, so next is very simple, same thing. So we consider velocity, now we consider momentum. So if you have the velocity defect, you will also have the momentum defect. Momentum defect means mass flow defect multiplied by velocity, extra velocity, it will give you the momentum. Okay, so this is the thickness theta we consider, is the definition as the distance, as same thing that we are saying that again, the distance that you have to move to compensate the total loss of the momentum. Okay, is my way. If you want to replicate the total loss of momentum per second, how much distance you need to move? This is the momentum thickness. These all are dimensions, thickness, okay? You have to consider additional dimension that you have to consider. You can see it may be defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced or moved to compensate for the reduction in the momentum, or you can say that to compensate the momentum defect. Okay, so this is the same. So I will not go again the similar thing that you can consider. This is in case of momentum thickness. So sorry, this is a mass flow rate. In case of momentum, if you say momentum, you need to consider multiplied by u, because the mass flow rate multiplied by u, that will give you the momentum. Okay, so you can see the difference here, u rho u dy, in this case rho u square dy. So now what is the loss here? So loss is you need to consider free stream velocity multiplied by u, capital U. So instead of u square, you just split it as these two, because these are the two different cases. So u square means this one is actually we multiply it. The lever in this case is u. It means the distance from here to here. But fortunately, in this case, your u is u infinity, your lever, it means the multiplication by u infinity. Okay, in case of ideal flow or uniform flow. But in this case, your what can I say, your infinity, the free stream is u infinity, but your lever is u, because your local velocity is not u infinity. So that's why we have two different, you cannot write it u square. Okay, so similar way, infinity minus actual, that will be the loss. So you can see this loss is here exactly same, is same, but we multiply by the lever because we need the momentum, right? So momentum is the local velocity, is a u, not u infinity. Don't put u infinity here because your local velocity is u. So what we'll have, this is the total loss, right? If you integrate, you can give some time, it's very simple. Integrate from 0 to this much, you will get the loss, momentum defect or momentum loss. So if you just consider the similar way, this is the ideal case or uniform flow. If you consider theta, in this case the additional thickness to compensate the momentum defect, so that should be equal to the defect. So this should be equal to the defect. So in this case, just simplify it, you will get theta like this. So you can see that either is delta star or theta is all are actually a function of u by u infinity. And you know that u by u infinity is always a function of f should be a function of y by delta. Okay, so if you replace this one in this expression, you will get another expression in terms of y delta. So theta can be represented by in the form of u by infinity. It can also be represented by in the form of y by delta. That's the problem that I gave you in the previous slide, okay, in the last class. So you just need to replace the expression and you need to integrate. That's the thing, you no need to do anything more than that. Shape factor, again the same, is just a ratio because is the boundary layer to determine. Okay, so the nature of flow, as I said, but this is not the parameter that we use to define the where is the Reynolds number, to define the laminar transition or turbulent flow. This is just to understand the flow, nature of the flow. Okay, so this is the same thing that I put here, but I already explained. Please read it. Okay, so the shape factor, the energy thickness, this is the, I just showed it last time, but this is same. Okay, so how much distance you need to measure perpendicular to the boundary to compensate the reduction of kinetic energy, to compensate the reduction in the kinetic energy. Okay, that's all. So kinetic energy is half mv square. So how much is the loss? Because you have the loss in here, so you will also have loss in the kinetic energy. That's the energy thickness. So you can see here, so kinetic energy is half mv square. M is equal to rho v, or this is a flow rate. Okay, it should be rho av. So this one is rho velocity and dy multiplied by 1. And what else? You have the u square. So this is the main definition of the mass flow rate. The kinetic energy due to the mass flow of m. So in case of normal case, that is the u infinity case, you should have before entering the boundary layer, we will have this much, right? So we have half rho u dy u infinity square. Same like before, we have the loss. So how much is the loss? We have half rho u, this one infinity, minus u square. Okay, so this should be u because this is local. So this one will change, right? So the loss will be half rho u, this much. You can just spend 5 or 10 minutes, you will understand. The same. So now it should be equal to, the effective, the thickness that you have to consider to compensate the kinetic energy difference. So that should be half rho infinity infinity. That is the infinity here. You can see, because in case of ideal case or when we have the free stream velocity, it should be u infinity. Okay. On the other hand, why is u here in this case? Because it's a local, because we are considering the real fluid, so you have to consider the local velocities u, and that u will change. Okay, that's why you need to integrate. You need to integrate because u infinity is constant, but u will change. That's why you need to integrate for different y. It means different height from or different distance from the wall surface. You have different u. You have to put the value and then you integrate. If the values are given, then you can get the some particular numerical digit. But the values are not given, you will get an expression. It depends on the problem. Okay. So the thing that you have to confirm that you should not mix up with the u infinity and u. In case of ideal case, you all have u infinity, there should be no problem. But when you have the real case, if you put u infinity, then it will be mixed up. Okay, you have to understand why is u, where is u infinity. These things you should be same. This is the ideal case, and this one is the real case. So this you should expect this one, but you will get this one. So how much is the loss? Okay, so if you equal it and simplify it, you will get this energy thickness. Okay, so how is different? You have u square by u infinity square, then you have u infinity. You need to write it down, write down this one, and theta, and h is the ratio, should be okay, and this much. If you have these three expressions, put it in your mind so that if someone is asking you to solve the problem, you can solve. Okay, so where is the difficulties here? Okay, I will try to help you to give you the start, then you can calculate. I think last time this problem, as I said, that you have these values given. So displacement thickness, how much is the displacement thickness? So your theta, sorry, not theta, should be delta star, right? Okay, so your delta star will be 0 to delta 1 minus u by u infinity dy. Now what you need to do, now you just substitute this value y by delta, okay, and then dy. Then you just integrate. If you have difficulties to integrate directly, you can just split it like this, dy minus 0 to delta y by delta dy, right? So then you just integrate this one. How much is 1? Delta minus 0 should be delta, then minus this one, it should be 1 over delta, and then you have the integration of y, so y square by 2, right? So in this case I don't have enough space here, so this should be delta minus you have 1 over delta, and then you have what, delta square, it should be half, right? Delta square by 2. So what you will have, delta minus you have half delta, right? So this should be delta by 2. I'm not sure my calculation is okay or not. You can check, okay, because I just solve it here. So what you need to do, just put the values, integrate, you check it by yourself, okay, and I think it's okay. So I just put the value, 1 over delta is constant, your y square by 2 should be 1 over delta minus delta will cut down, yeah, this like this. And how about the momentum thickness? You do it by yourself. Okay, in case of momentum thickness, you know that the theta, you will have the another u by u infinity, so you can multiply it in that way. So please solve the problem, okay, and let me know whether you can do it or not. How about this? Same. In this case, I just put it's very simple y by delta, but you will have three expressions. You have to integrate, split it, integrate it, and sum up. You will get the values. Okay. Please try to give me the feedback of your results. So in this case, your expression will be something. As I said, you can see here. In this case, if I want to write it like this, delta star by delta should be half, right? This one can be written as is delta star by delta should be half. So this one you have, well, how much is this? Delta star by delta should be how much? You need to write it down, or you need to calculate how much. Similar way, when you have this theta, should be how much delta. There should be no star, okay, this should be delta, I think. So you need to find out theta by this much. How much is this? Okay, so you have to calculate this too. I'm giving you the last time. Okay, so those students who are not following up, you need to solve this problem and keep it for the future reference later on, so that when you can revise, you can actually have a look. Okay, you can also discuss among yourself, should be okay, because it's not uh, 1 minute. Okay, so these two problems you have to solve, and also I uploaded one tutorial. Oh yeah, you have class at 12, I know. Okay, so I will end up the class. Hold on.